Okay, we can start now. Welcome everybody to the first session of the Quantum Computing for Quantum Chemistry workshop inside the Quantum Week of Fun. I'm very pleased to have here as our first speaker, Kosuke Mitarai from Osaka University and QNASYS, who is going to talk to us about, I think, would be a variety of interesting topics regarding the variational quantum eigensolver. So Kosuke, whenever you are ready, you may go.
Okay. So yeah, thank you for the introduction and thanks for having me in a great workshop. So what I'm going to talk about in this talk is how we can extend the variational quantum eigensolver from its original form to like more practical applications. Yeah. So this because this is the first talk in this workshop, because so I decided to put something about NISQ on this slide, although you all may know what NISQ is, but so the current quantum computer is called NISQ, which is an acronym for the noisy intermediate scale quantum devices, and it consists of some few tens of qubits or 200 qubits, but you can only use some hundred of gates to the depth, right? And as you know, the NISQ is really noisy and it cannot execute complex circuit like the ones used in the HHL algorithms, like where you can solve many interesting problems using linear system solver. But so we need some scheme for applying NISQ to some practical problems other than these complex algorithms. So yeah, this circuit is really hard for NISQ device because it has tons of gates in it. So the most famous algorithm for NISQ application is called quantum classical hybrid algorithms, in which we use a shallow quantum circuit which can be executed on the NISQ devices for solving really purely quantum tasks, and then give a feedback to the classical computer, which does other classically easy tasks. And this classical computer also feedback to the quantum circuit and solves a difficult problem together. So why we use this is because we think that meaningful computation is hard for current QCs. So we really need to pass classically easy tasks to classical computer. So because this workshop is about quantum chemistry, I'm gonna dive into the quantum chemistry application of NISQ, and the most popular and famous algorithm for applying NISQ to quantum chemistry is the variational quantum eigensolver. And I think you might all may know this algorithm, but for completeness, I will explain the details of this VQE algorithm. So the VQE is the algorithm for finding ground state of a given quantum system. And it works like this. So we have some molecule or some quantum system that we want to find a ground state of, and we encode this quantum system in Hamiltonian H. And we do something like this. We use a parametrized quantum circuit, which has parameter theta here, and execute this quantum circuit on the NISQ device to get output state, which I put it here and psi out. We measure this psi out state to get the expectation value of some Pauli operator, and then we sum up those Pauli operators to get the expectation value of Hamiltonian H. So because we want to find the ground state of a quantum system, we try to minimize this Hamiltonian H by updating this parameter theta iteratively to minimize this H expectation value of the Hamiltonian. And if we loop through this loop like many times, we can make the theta converge to some optimal theta, which I denote the theta star. And you can get approximate ground state of Hamiltonian as this psi out with the parameter theta star. So what is promising about this VQE algorithm is that classical computer cannot generate this state generated from the NISQ quantum circuit. We believe that simulating this quantum circuit is really hard for classical computer. So it might, because we don't know for sure, but it might allow us to analyze more like complicated system than before that can be done on the classical computer. So, but VQE itself, like original VQE original VQE algorithm was to find the ground state energy and the ground state, but only ground state energy is not really enough for practical applications. For example, like energy gaps and transition amplitudes are really important in, for example, for photochemistry. So you want to find the energy difference between the ground state and excited state, or you might want to find how the ground state responds to some perturbation, which is this described by the operator A here, to find like absorption ratio of the visual light. And also energy derivatives are really important for example, geometry optimization of molecule. For example, you can use energy derivatives between this with respect to this nuclear distance to find the equilibrium position of this nucleus. So let me dive into the main content of this talk. So first, I'm going to talk about how we can generate the excited state on the quantum computer using the framework of the VQE. So first, I'm going to talk about like existing algorithms for this excited state calculations, and then I'm going to talk about the algorithm which we propose, which is called Subspace Search QE, and also I'm gonna talk about our recent work about benchmarking the different methods for excited state calculations, and then secondly, I'm gonna talk about analytical derivative sampling for the VQE. So first, I'm going to talk about finding excited state with the VQE. So existing works for the excited states is like the first one is the variational quantum deflation, which is introduced in this paper. So if you are interested, you should read this paper. But so the idea of this algorithm is to find the eigenstate of the Hamiltonian H by sequentially searching for the orthogonal eigenstates of the Hamiltonian. So you define the new Hamiltonian using original Hamiltonian plus the projector of the lower energy eigenstates. So if we perform this, if we perform the VQE of this Hamiltonian HK, you can obtain the circuits UK such that this UK produces the case excited state of the Hamiltonian. So the requirement is that we have to take expectation value of this Hamiltonian. So we need to measure the overlap between the eigenstates, and also some possible problem is that the evaluation of this transition amplitude, which is really important when you want to analyze some response properties, but this evaluation is not really straightforward. And the second one is quantum subspace expansion, which is introduced in this paper. So this method is essentially the combination of the configuration interaction method that is used in classical quantum chemistry with the VQE. So this method firstly perform the VQE or usual VQE on the target Hamiltonian and obtain ground state psi. And secondly, it applies excitation operator to the psi and measure this kind of transition amplitudes. And then you have a matrix representation of the Hamiltonian with respect to these bases. So you can diagonalize this Hamiltonian matrix to get some of the excited states. So for requirements of this method is for chemistry problems, for example, naively, you need to measure the 3 RDMs in my understanding. So you really need to measure many terms to do this algorithms. I think if you really need a 3 RDM, you need order n to the 6 and n to the 6 measurements to perform this task. So to improve those algorithms, we think about our idea is to do something like this, which I explain in this slide. So the original VQE uses a single input state, and then it gives a single output state, and you minimize the expectation value of the Hamiltonian. So in the SSVQE, which we propose this, we use the two or more orthogonal states as the input, and you apply the same circuit U theta to get two output states, psi 0 and psi 1. And you can see that this unitary, because this circuit is unitary, and the input is orthogonal, so that this output state is always orthogonal. So if we minimize this averaged energy with respect to these two states, you can find if this loop converges, you can find low energy subspaces, because low energy subspace of this Hamiltonian. So that's why we call this method the subspace search, because after convergence, this psi 0 and psi 1 is in the somewhere in the low energy subspace. So more concretely, the subspace search VQE works in the 2 steps. So the first step is to do the minimization of the averaged energy to get the low energy subspaces. And the second step is to find, extract the eigenstates from low energy subspaces. Generate the superposition of this input state. You can actually make a superposition of psi0 and psi1 at this output state. And then if you maximize Hamiltonian expectation value of the Hamiltonian in this using this state with respect to this parameters alpha and beta, you can find a first excited state of this Hamiltonian because we have that psi0 and psi1 is somewhere in the subspace spanned by the ground state and the excited first excited state. Yeah. So if you maximize it, you get the first excited state. We can also construct a single step version of the system QE because if we can introduce a weight Wi in the cost function, like so we input the 2 state and we get the two output state, and we combine them using the weight Wi. So if we set the W0 larger than the W1, then we can expect, because W0's effect is higher for this cost function, we can expect that psi0 converges to E0, which is ground state, and the psi1 converges to the first excited state. And so I note that this. So for simplicity, I use the just two inputs, but this approach is not limited to the 2 states. But if we use more states as the input, we can find more excited states. Like in general, like EK, which is a kth excited state. So possible advantages of this subspace search VQE is that we don't need to measure the overlap between the states because this output state is always orthogonal, because U theta is unitary and the input is orthogonal. Also, it only requires a measurement of the Hamiltonian, which is in contrast with the quantum subspace expansion, which needs some measurement using like 3RDIM. Because in subspace search VQE, the cost function is just the expectation value of Hamiltonian. And also, this SSVQE is an amplitude of the between the 2 eigenstates, which I will talk about in the later slides. So also we perform this. We perform the numerical simulations to check the validity of the Ising model using the Ising model. And yeah, you can see the energy converges to the desired value using in the as you iterate through the optimizer. And yeah, in the step 1, the energy converges to the average of the low lower energy states, and in the step 2, the energy converges to the highest eigenstates in the subspace. And this work is in this paper. So if you are really interested, you can find the details in here. And as I mentioned, the subspace search VQE is really, and in subspace search VQE, we really easily evaluate the transition amplitudes. So how we do this is like this. So after the optimization, we have the 2 input state, which becomes ground state and the first excited state. So we can find some alpha and beta which can generate the superposition of between this A0 and E1. And if we define this kind of states, you can find really, with a really simple algebra, you can find this plus state expectation value of A and the minus value of expectation value A is leads to the transition amplitude of the between the EI and EJ. So what we have to do is just measure this plus expectation value and the minus expectation value, and we can just subtract them to get the desired quantity, which is transition amplitude. So I think that I have to mention the multi-state contracted QE at this point, because this algorithm shares the same idea with the VQE. This method is introduced in this paper, so if you're interested in this, look at this paper. But so this MCVQE algorithm also works in 2 steps, and the first step is exactly the same for with the subspace search VQE, where we find a low energy subspace using the orthogonal input states. But at the second step, MCVQE differs from the subspace search VQE, because MCVQE, we measure the matrix element of the Hamiltonian in this low energy subspaces, and we classically diagonalize this Hamiltonian. And yeah, and you can find the eigenstates using this diagonalization. And so I've gone through some of the several methods used for the excited state search and the VQE. So I'm going to present some our recent work for comparing those methods. So what we compare in this work is variational quantum deflation, which we abbreviate to VQD. So as a reminder, in the VQD, we sequentially find the eigenstates using this kind of Hamiltonian. And we also use the MCVQE, which as I mentioned, which finds a low energy subspace first, and then diagonalize the Hamiltonian matrix in the low energy subspace. And the settings of this benchmark is we use a diazine molecule, which gives us the 6-qubit Hamiltonian after active space approximation. And it is a kind of a model molecule for photochemistry. I'm really not professional for the chemistry part, but joint research. As a joint research, we have learned this kind of molecule. So we use so for the ANSYS circuit, we use a particle number preserving circuit, which is described as like this circuit. And this circuit preserves the number of the particle, or number of electrons in the wave functions. And okay, this is a mistake, but we fixed we fixed the d to the d equal 20, not 140. It's too much, but d equal 20 for our methods. And we used noiseless expectation values. We didn't do any sampling, or we didn't introduce any noise or whatever to do this, but we just use exact simulation of the quantum circuits. So the result looks like this. So we draw the potential energy curves of this molecule, varying structure of the molecule, and this is the result of the subspace search VQE, and this is the result for MCVQE, and this is the result for VQD. And the dashed line is the exact solution, and points denote the result from the VQE. So as you may see, SSVQE is not really working right, because and it can be clarified by using the deviation from the exact energy. So in this plot, we plot on the vertical axis represents the error from the exact value, and the dashed line is the chemical accuracy, which is defined as 1 kilocalorie per mole. So for subspace search VQE and MCVQE returns almost the same result, but VQD performs far more better than these two methods. So we can say in this setting, the VQD performs better than the others, but we suspect that the reason for this is that VQD can use the different circuits UK for different states EK. And this is in contrast with the SSVQ and the MCVQ, because these circuits use the same circuit to generate all the eigenstates. However, so we find that VQD is the best method for in this settings, but in VQD, the evaluation, as I mentioned, evaluation of the EI, AEJ, something like this transition amplitude thing is not really straightforward. So in this paper, we introduced some method to evaluate this quantity using VQD. So to evaluate this transition amplitude in VQD, a naive approach will be something like this, where you use controlled UI and controlled UJ to evaluate this transition amplitude between the EI and the EJ. So, but this UI and UJ is a circuit which is a result from the VQE, and it is really complex on its devices. And it is really hard to make controlled UI in UJ as you expect. So we propose the method to extract this transition amplitude using a post-processing similar to the one employed in the Subspace Search QE. Like so how we do this is that we use we first apply UI and then apply Al alpha, which is a certain Pauli rotation gate, and this Pauli rotation, the generator of this rotation gate is the Pauli operator, which appears in this operator A, and then we apply UJ dagger, and then take expectation value and post process them. So this circuit is really similar to the overlap measurement, which we use UI and UJ dagger. So this circuit is really this circuit has really low cost compared to this complex circuit. So let me summarize this first part. So the first part is a proposal of the SSVQE subspace search QE for the excited state. It guaranteed orthogonality at the input, and you can evaluate very easily in the benchmarking work. We find that the VQD performs better if we use the answers with the same steps. So we constructed the method to measuring a VQD, actually. Yeah. So this is the summary of the first part. So the second part is how we analytical derivative for the VQE. And this is in this paper. So if you are interested, you can go online to this paper. So the motivation of this work is because we already found the ways to search for the ground state and ground state and excited state, and also the transition amplitude using these VQE, the SSVQE or VQD methods. What was remaining was that calculating these ground state or so in the geometry optimization position, or to calculate the polarization, we need a derivative with respect to the electric field, and also if you want any more chemical shifts, we want magnetic field derivatives. So the construction of this technique is that the first one is a textbook formula of energy derivatives in chemistry, and which is available in like a standard or maybe advanced parameter shift load, which I think is becoming popular now, which can extract the derivatives of the wave function of parameter quantum circuits. So combining these two, we can find the analytical derivative of the VQE energy. So first, I'm gonna describe what the parameter shift load is. So suppose our parametric quantum circuit is in this form, like so the answers consists of some gates and some gates, and all parameters are implemented as rotation angles of the Pauli operator. Then we can evaluate the derivatives of this output expectation value by using this two circuit. We shift the parameter by pi over 2 and also minus pi over 2 to get the derivatives like this. So you measure the expectation value of B using this circuit and also by this circuit, and you subtract these B plus and B minus. And then you get the analytical derivative of the expectation value of B with respect to some parameter theta k. And it can also be generalized to higher order derivatives straightforwardly. So analytical derivative, to get the analytical derivative, we describe settings we assume in this work. So we assume that the situation just follows. So Hamiltonian depends on the parameters, some system parameters X, which can be nuclear position or electric field or magnetic field. So we can write the Hamiltonian like this, and it can be decomposed into some sum of power operators, and this coefficient depends on the parameter X. So, and we assume that for a given target point X, we already know the optimal VQ parameters, which I denote as theta star, which is dependent on X. And in this situation, what we want is that if we define E star X as the optimal parameter, optimal VQE energy at the point X, we want some d derivative of the E star with respect to this parameter, system parameters X, in which can be written like this, right? So the first derivatives, it is really straightforward. So if the VQE solution is variational, like which means that the gradient between with respect to the theta is 0 at theta equal theta star, you can just write down the equation like this, which is called the Hellman-Feynman theorem. This is famous. So yeah, so we can calculate this derivatives of Hamiltonian and measure this expectation value with respect to this psi theta star. You can get the derivatives of energy. So I think the important note is that in usual VQE, we use second quantized Hamiltonian only. So VQE wave function does not very explicitly depend on basis functions. So something called play term does not appear for this task, because variation in the basis functions are can be fully contained in the variation of Hamiltonian Hx, and yeah. So we do not really need to consider the change in the basis function explicitly in this approach. So as I said, the first derivative can be calculated. The first derivatives of the Hamiltonian can be calculated on the classical computer. I assume maybe it is assumption, but I believe this is feasible on the classical computer. And then if you write down this equation by plugging this into this thing. You find that derivatives of energy can be evaluated by summing up the Pauli expectation value Pauli operator using this coefficient. So the first derivative is really easy. That we can just evaluate the expectation value of Pauli and sum up the values to get the derivative. So it corresponds to the evaluation 1 and 2 RGMs. And for the second derivative, it gets a little complicated. So analytical expression of second derivative is something like this. And then this includes the response of the VQE optimal parameter with respect to the system parameter X. And this thing can be obtained by solving this equation, which is called the response equation. So the thing that we have to evaluate on the quantum computer is these things, and this and this, same, and this and this. So each term can be evaluated by, as follows. So for this term, we can just measure the second derivative of Hamiltonian, and we can just measure, which means we can just measure the Pauli operator, expectation value of Pauli operators. And for this term, which is a cross derivative of the system parameter and the VQE parameter, but we can just write it down as this, and which consists of the derivative of Hamiltonian coefficient and multiplied by the Pauli operator derivative. So this Pauli operator derivative can be evaluated by parameter shift rule, which I mentioned earlier, and also the second derivative with respect to the theta can be evaluated using the parameter shift rule too. So yeah, for the remainder, parameter shift rule is something like this. You can just shift the parameter pi over 2 and minus pi over 2, and then subtract them to get this. So the measurement of evaluation of this term and this term is really easy for using this technique. Yeah. So to summarize the second derivative evaluation, to evaluate this, we evaluate the Pauli operator and the derivatives of Pauli operator and the second derivative of Pauli operator on the quantum computer. And also we calculate these Hamiltonian coefficients on the classical computer. And finally, we plug those values into this formula and solve the equation, and we get the second derivatives of the energy. So we validated this this theory by a simple simulation using a hydrogen molecule, which is really, I think it's really popular testbed for the VQE calculations. So we performed the numerical simulation to validate the theory, and we find that it is really, it works very well. And also, I'm not gonna talk about in details, but we also applied this method to the orbital optimized unitary coupled cluster. And I think the later talks are on this topic. So this orbital optimization, for orbital optimization, you may want to go for the later talks. But yeah, this technique reduces the hardware requirements, and we developed orbital optimized unitary coupled clusters and applied the derivative theory to perform the geometry optimization in this paper. So for if you're interested, you can go to this paper for details. So for the second summary of the second part, we have developed analytical derivative theory for the PQE, and we have tested the method with really simple calculations with a simple hydrogen molecule, and also we tested it with the orbital optimized unitary coupled cluster, which is more sophisticated method, and using the ammonia and water molecule. So, okay, so I have talked about this talk, but well, yeah, that's it for my talk. Thank you.
Thank you, Kosuke. It was a very interesting talk, very, very interesting. I'm going to go to the Slack channel. Well, something very interesting happened, which is that some people made questions and then other people from the audience answered them. So it's kind of silly.
Okay.
But I'll go directly to the ones that haven't been answered yet. And then if we have time, I'll go to the other ones. So yeah. Alex Thom asks, it seems that finding the best theta to convert the input states into the best possible output states is very much dependent on the quality of the input states. Have you looked at this dependence?
So, well, what was the question? The quality of the input states? Depends.
I'll repeat. So finding the best angle to convert the input states into the best possible output states, depending on the quality of the input states. Have you looked?
Yes. No, not really. I haven't looked at it, but it's really a good question. And yeah, like for the subspace search VQE or MC VQE, we really need orthogonal input states to get the correct solution. So yeah, this is I think that is really that is a problem that was really exploding, I guess.
Alex also does a similar question for the derivatives. So is there dependence on the input states which needs to be propagated through the derivatives?
No, not really, because this does not really depend on the input state, because we just need to evaluate those derivatives between with respect to the parameters, and this derivative does not really the accuracy of this evaluation does not really depend on the input state. But maybe if you use a different input state, you can find more accurate solutions for the PQE. But this is not the focus of this topic. So I don't think the input state does. I don't think the input state does affect the quality of this approach.
Mm-hmm. Okay. I have a question myself regarding the subspace BQE, which is so you mentioned that the accuracy in general is a bit worse than variational quantum deflation or QCxQC.
Yes.
But does this accuracy depend on the number of states you are considering in the calculation?
Yes, I guess so. Yeah. So because SSVQE and the MCVQE tries to find a unitary that maps input state, multiple input states to multiple output states. So if you want to find more eigenstates of the Hamiltonian, you really need you really need to implement more parameters or more complex answers for the unitary circuit that is used in the VQE process, I guess. So yeah, the answer to the question is, I think, yes. It does depend on the number of parameters, a number of the eigenstates that we want to measure.
Okay. This question from Nathan Fitzpatrick reads, you mentioned you wanted to gradients for NMR properties with respect to the field. Are you planning to work on this in the future?
Yes, not really myself, but my collaborators are, I think, working on this topic, I guess. Yes.
Okay. I'll ask another question, which is, I noticed ansatz you used, this particle number preserving ansatz used in the first part of the talk.
Yes.
I found it interesting because it's neither any couple cluster derived ansatz and it doesn't have the typical structure that I have seen in other Hadamard efficient ansatz. Can you comment why you chose this ansatz?
Because we are considering like a exact simulation of the quantum circuit. So if you use a particle number preserving ansatz, you just search for the subspaces where the electron number is constant. So this really helps to find a good solution for the parameters. And actually, if we have tried the hardware efficient ansatz in this benchmark, but it doesn't really produce good results for this task.
Okay, thanks. A question from Peter M. So I guess it's an easy one. Are all your papers on the archive?
Yes, it is on archive. You can search. You can search by my name, maybe. Yeah.
Good. Thanks. And then Marco Di Gennaro asks, how do the different methods scale with the number of atoms?
Okay, that's a little hard question to answer. But so in general, the VQE doesn't. I think that in general, we cannot say anything about the scaling about in the VQE algorithms because I think no one knows how it scales with the system size. Maybe because the NISQ devices are noisy. Maybe it does not really scale to the large systems. But yes, so the answer is I really don't know, but that is the direction I am really working for, like how we can benchmark the scalability of the VQE.
I guess also my impression is that there are many things to balance in terms of you start to increase the circuit depth, start to increase the number of parameters to optimize.
Yeah. There's so many parameters, so we have to pick some, we have to pick some parameters and then vary other parameters to get intuition to how it scales.
Okay. I have another question from Nathan Fitzpatrick. Do you have any other plans for the response properties you have worked on? For example, green function methods or things like that?
Well, so I think for the green functions, we have not myself, but the researcher at QCxQC has a paper about the green function, and also we are also working on the adiabatic couplings too, I guess. So yeah, we are really working hard to, making those, I guess, practical quantities calculatable on the QE.
Mm-hmm. Good.
Yeah.
Question from Hans Chan, reading now. Thanks for the talk. Sorry I may have missed an early question. Will the analytical derivatives work on excited states and that's parametrized with BQD?
Yes. So because what we assume is that in this setting is that we have optimal variation, optimal BQE parameter which gives zero gradient for the energy, and I think the variational quantum deflation or VQD returns something like this, like returns some parameters like this. It gives a parameter which is very variational. So that means that these discussions applies to that approach too.
Okay, thanks. I don't know if there are any other questions.
I guess all the questions are answered in this section.
Yes, seems that. Hans replies, I'm guessing you will need to apply the orthogonal constraint when evaluating the gradient.
But I don't really understand what he means by the orthogonal constraint for the derivative.
I'll ask Hans to elaborate. Hans is writing. For VQD, the overlap has to be evaluated.
Yes.
So will the analytical derivatives work on the excited state and such thing though that you have to evaluate the overlap?
Yeah, I think you also have to evaluate the overlap. That so the derivative of the overlap that can also be evaluated using the response equations, I guess. Because if we can solve for this theta star differentiated by xi, I think you can find a gradient with respect to the gradient, or all those responses of the overlaps.
Mm-hmm.
I think I mentioned it in the paper, so if you are interested, you can go onto the paper to see the discussions.
Okay, it seems there are no more questions.
Okay.
So basically, thank you again for this talk and for answering the questions. Very nice. I'll contact you later regarding the Slack channel in case you want to comment and answer other questions.
Thanks.
So, well, thanks a lot.
So, yeah,
And,
yeah, thanks a lot.
I'll see you around.